Welcome to this webinar on air quality forecasting. I'm Fabien Brocheton from Numtech company. This webinar is done in the framework of the EVEREST project funded by the European Commission. And EVEREST project wants to develop a design environment for HPC and extreme scale big data, and you can see more detail on the URL provided on this slide. In this project, there is 3 use cases, 2 based on weather forecast, one on energy prediction forecast from wind, and another one on air quality monitoring. And the third use case is about traffic modeling in cities. So in this webinar, we will speak about the air quality use case. So the planning is just to give some information on air quality challenges, air quality modeling, and especially air quality operational systems, and what we do or want to do in the EVEREST project. So air quality challenges. So here it's some key facts from the World Health Organization, but you can see, I'm sure, a lot of things like this. What the World Health Organization says, it's clearly air pollution is one of the greatest environmental risks to health today, and especially if we consider the last line, 99% of the world population live in a place where air quality pollution is above the guidelines, the last guidelines of the World Health Organization. So it's a key point. But air pollution is very complex because it's a mix of, we can speak about various pollutants. So you can heard about particulate matters, ozone, SO2, NOx, but in fact there's 100 or 1,000 compounds in fact in air pollution. It's also pollutants emitted from various sources, from cities, from industry, from agriculture, but also from the nature. So it can be vegetation, forest, ocean, and so on. We have a lot of physical and chemical interaction, and also we have a lot of impact, because when we say air pollution, it's also air pollution on human health, but on vegetation, on buildings, on quality of the water, and so on. If we try to determine the sources, here it's an example of the last report from the European Environment Agencies about the emission sources which drive air pollution in Europe. So you have different countries, different colors. So for example, in blue, it's that's in line with road sources. But what we can see it's in orange, we have industrial sectors, which remains a key sectors for, in fact, many all countries in Europe. And it's also what we see when we analyze not the emission source, but the action plans made by the different countries. And also in orange, you see that a lot of action plans focus industries. But for these action plans, we need numerical models to assess the impact of air pollution from these sources and evaluate also impact of the emission reduction strategy. So now some words about air quality modeling. So why we use models? Because as we already said, air pollution is very complex, but even when we focus only on emission from industry, we have a lot of parameters which leads to the impact of air pollution at one location. So for example, we have all the emission parameters. So emission parameters can be the type of the source. So is it a stack, the surface sources, the volume sources, the height of the emission, the speed and temperature of emissions, the amount of emissions, and so on. So here is just on the right one example when we want to see the impact at the surface of the air pollution from a stacks. So it's the red star here. So it's a stack with a given 8, and here it's the impact on the surface from the distance to the stacks. And we see that, for example, the stacks of 0 meters, we have a lot of impact on the surface, whereas a stacks of 80 meters, we have less impact. But here, it's for all other parameters which are fixed. For example, meteorology. After the emission parameters, we have also the meteorological parameters. The air temperature, the wind speed, the wind direction, the atmospheric stability. And here, at the right, it's another example to see the sensitivity of the air pollution impact. So it's always one stacks, the red stars, for the same emission parameters, but here for 3 meteorological condition, 3 atmospheric stability. And we see that from very unstable condition can have impact very strong close to the sources, whereas for stable atmospheric stability, in this case, which have impact much more away from the sources. And we have also the environment of the dispersion. If we have buildings, topography, land use. So here just to give an example, just to say, okay, we have the sources, the red stars, we have the buildings, and here it's just the difference when we simulate the impact when we have or not the buildings, and we have a lot of difference. So we need models because, okay, I see you some sensitivities, but just for variation of one parameters, whereas all the other parameters are fixed. But in reality, it's a mix of all these parameters which can lead to the air simulation. That's why it's impossible to do it with simple tables and so on, and models are also more and more complex today. What it is interesting is that, okay, we have models to make studies, but at the start of the 2000 years, we have some big industrial companies. We decide to go beyond studies, but to use air quality operational systems. So what are an air quality operational system? Just a layer, a software layer, which manage, in fact, all input, the computation and produce output automatically. So in real time, so it can be every hours, every 10 minutes, and to produce also forecast. So it's typically, so it's just a system for which we get some input data, so especially the meteorological data and the emission data, to run an air quality models and to produce some maps, some charts, and so on. And the objective of these tools, first, is to know its impact in real times, to be able to generate reports on daily or monthly scales, and not as a study, for example, every year, to identify also more easily which sources are responsible of the impact of the seeds. Communication with the neighbors, because when you have your impact in real times, you can, for example, more communicate with your neighbors, especially when we speak about odors, pollutions. And for the forecast modes, the objective for the sites was to adapt its impact according to the meteorology on its activities. That means even the forecast systems, you have impact on air pollution, to be able to manage your emissions in order to reduce this impact in reality. To do that, especially for the forecast part, you need, before to have air quality forecast systems, a weather forecast systems, which are before specific to the industrial site. And what is also to have in mind is that the performance of the air quality forecast is mainly driven by the weather forecast, and the weather forecast represent more than 90% of the full execution times. So what is a specific weather forecast chain? So it's what we can say a cascade rate. You have meteorological models which have some inputs. So what are the inputs? In fact, the inputs are the global forecasts. The global forecasts are performed by national centers. So it can be, for example, in France, Météo France, but it can be also the European centers of meteorological forecast. It can be the US meteorological forecast centers. It's also all the observation you can obtain from the weather organization. So it can be in surface, it can be radio sounding and so on. And from this input, you compute weathers over a specific domain. And in fact, here you have resolution of about 50 to or 25 kilometers. So you cannot go directly from this resolution for simulation of 1 kilometer. You need to have some steps to manage some process, and also due to numerical schemes. So generally you have different kind of size domains. So for example, one from Europe, one from France, and the final one for the industrial size you focus. And if we consider these systems, in fact it works. So it's what we do in Numtech from now 20 years. And here it's an example of for a Total energy refinery in France. So for which before the operational systems there are, so here we speak SO2 peaks of 300 microgram per meters cube. So you have more of about 40 peaks during the years, and we see that with the application of the systems we have a clear reduction of the peaks. But there remains peaks because first you cannot control all your emissions. You can have incidents. You have some meteorological conditions for which even if you reduce as much as possible your emission, you will have an impact. And we have also false forecast. So false forecast can be of different kind. So when you consider that for these big sites the emission forecast is well known, the main false forecasts are false weather forecasts. So here the figures are only numerical forecast, and the circles is numerical forecast at location where you have air quality measurement station. So in this case here you have strong impact at the north of the sites. So here it's the orange value, but it's false predicted peaks because when you see after the observation here it's green. So the wind direction is good and so on, but for example the atmospheric stability is not a good one because here you have forecast strong impact compared to the observation. Here totally at the right it's the reverse. The wind direction is also good, but you have a green forecast, whereas the observation is orange. So it's the reverse. Here it's under prediction of the reality. And in the middle, it's another kind of situation because the forecast is wind from north to the south, whereas in reality you have air pollution on the north. So in this case, it's errors on wind direction forecast. We need to provide this forecast, And that is important also to see that today we are in new context, because in the start of the 2000 years, okay, we have very few big industrial sites which can pay such operational systems. But today we have more and more new sites to follow for many reasons, especially the social pressure on industrial sites. More and more sites, but also more and more kind of sites, because before we speak about refinery, big chemical plant, big electricity production plant, but we have also now more and more small plants. For example, sewage treatment plant for odor pollution and so on. From financial part, we need also to mutualize cost more and more. And what is important also, that compare that we have 20 years ago, it's easier to deploy local weather observation at one industrial site, and also to access some new global weather observation from rain radar, from satellite, and so on. So we have a clear change of vision from deploying a specific weather forecast chain for one industrial site to have more generic weather systems, typically at national scales, to initiate different air quality forecast systems. And this is the main core of the air quality pilot use case inside EVEREST, to have a national weather forecast systems, in our case over France, using the WRF models. So WRF, it's the main mesoscale models used for weather forecast. And this national weather chain initiate different local air quality dispersion forecasts for different industrial sites. So you have a transfer from the national scales to the local scales, and after you have a different air quality computation, in our case using the ADMS models. And the objective of EVEREST is to improve the forecast of air quality for each site, especially to avoid false decision. Because when we have false forecast, for example, you say, okay, we have a big impact, so you need to reduce the emissions, and if the site applies some emission reduction, this has a cost, and the cost can be high. So the objective is to really reduce false decisions, and also for this full chain to have a delivery time as short as possible. And have in mind that the air quality forecast is mainly driven firstly by weather forecast. As we have seen, we can have error on wind direction, error on atmospheric stability, and so on. And this part here is more than 90% of the full execution stack. So in the EVEREST application, we have a main focus on weather forecast on these two parts, national forecast and local forecast. So the EVEREST challenges for this air quality use case is various. So as we have said, we have a first focus here on the national WRF chain. So the main key point is to reduce the WRF execution times using, for example, FPGA application. So you will have specific seminar from CHIMA on these topics. It's also to improve the quality of this WRF forecast using, for example, assimilation, using global forecast from European centers, and so on. So you You will have also a seminar on this part. At the end, it's the main core of the full EVEREST developments to have a design environment to manage heterogeneous application and so on. So for this orchestration and design environment, you have different seminars on this part. And we have here the local weather forecast part, which are the following of this presentation. And in this case, it's based on a machine learning approach. For this local weather forecast, we decided to apply a machine learning approach, which is a combination of what we call an ensemble forecast, so mixing different deterministic weather forecasts forced by local weather observation on site in order to have a better local observation at one industrial site where weather observation is available. In our case, the machine learning approach is a ridge regression approach with discounted loss method, and the objective is to minimize the root mean square error between the aggregated prediction and the observation over a period. Not what we speak also of a downscaling approach in our case, because the different numerical forecasts have a spatial resolution of 1 kilometer or above compared to local observation, which is really a point. So why we use ensemble forecast and not only the best deterministic forecast? First, not during the calculation, but in reality, meteorological processes are naturally uncertain. And the consequence is that in weather simulation, we have in some parts some random computation. Secondly, we have also uncertainties in models due to the initialization, the forcing data, due to the physics we introduce in the model, due to a numerical scheme we use to resolve this physics, and so on. So the best model is not necessarily the best model with the best spatial resolution, the most recent numerical scheme, the most complete physical parameterization, etc. And also considering that when we say the best, generally it's also the worst in terms of execution time, which can be limited in operational forecast. That's why an ensemble is better to capture the best forecast from each members according to the current situation. So now, what are ensemble? Ideally, it's using various models, different configuration inside these models, different initialization, and also what we call combining cycles. So cycle is the start of the forecast during a day. In practice, even big meteorological national centers has no sufficient HPC resources to have such a very large ensemble. Generally, for example, they use only the same models with different initialization, different cycles, and eventually different configuration. In our case, for the ensembles, we do forecast for the 2 or 3 next day. We use different numerical weather forecast. One is performed by Numtech directly using the WRF models at 2 spatial resolution, 3 and 2 and 12 kilometers. The GFS global forecast, which are the US forecast, the French Météo France forecast, and of course the EVEREST WRF forecast, which will be performed above France. We use also, of course, local weather observation for each industrial site during the demonstration use case with hourly time series value, and the forecast it's also hourly forecast value. And since we focus on air quality dispersion, the weather parameters are first the wind speed and wind direction and the air temperature. There is no simple measurement of atmospheric stability. So here just an example of what we obtain on wind direction when we apply or not the ensemble forecast forced by observation. So on the left is the best results from deterministic forecast. So the best, when I say the best results, is to take for each hours the best between the different numerical forecasts. Is not the best model, because there is no the best models. And at the right is the machine learning approach, and here the results are the root mean square error on 2 days of forecast over 6 months. So basically, when more we are blue, better the simulation is, because in fact 0 there is no bias compared to the observation, and more we are in red, more it's worst. And we see clearly that, of course, we would say, so yeah, it's reference, it's most simple to forecast this oceanic area, but here in the center, in the Alps, in the Mediterranean area, the forecast is has much more difference with observation, and with the machine learning approach we decrease these errors, and we are blue or light blue value. So I will present also another kind of curves which are not aggregated in temporal view, but what are the results, so which are also here the root mean square error for each Earth of the forecast. In this curve, so here, for example, it's the wind speeds forecast. The curve here is the reference forecast, so it's always the best deterministic forecast among all available numbers. So remember that, for example, the Numtech 3 kilometers is not necessarily the best one. It can be also, sometimes it can be the global forecast. And here will be the results of the machine learning approach for different option configuration of the machine learning approach. And the gray one is today the best configuration we achieve. So what we see, so here is the result for the wind speed forecast, for the air temperature forecast, and on the right for the wind direction forecast. So first, for the wind speed at left and the air temperature in the middles, we have good results. Of course, we see that with the time, the performance of the machine learning approach decreased, which means we have the best results for the next hour of the forecast, and after this increase, so it's especially the case for the air temperature. For the wind direction, it's much more complex, because what we see here, it's a very sparse results, and this is due to many things. First, there is uncertainties in measurements, there is uncertainties in simulation, and also when we speak wind direction, we have the low calm conditions, so the low wind speed. When we have low wind speed, generally we have uncertainties in wind direction, because direction is not is not very well defined, so much more complex to reproduce. So to finish, does this air quality use case a big data application? So if we skip the national WRF chain, which are clearly big data application because we combine different kind of input data, we calculate 3D or 4D data because 3D spatial 3D with 1D for the temporal forecast. So yes, WRF weather simulation is a big data application. So now on the local air quality part, on volume. Of course, if we speak only one industrial site, there is not so much data to manage. But the objective is to manage very large number of sites, ideally 100 or 1000. So in this case, we can say that we have large volume data to manage. Velocity is required because it's very important to have the results as soon as possible. Remember that it's to make a decision on industrial sites, so and also that some decision need times to be activated. Sometimes you cannot activate an approach in the next 1 hour or 3 hours. So it's very important to have the results as soon as possible. Variety, yes, because we combine weather 4D forecast with weather 2D observation, with also forecast on the emission. So I don't speak here emission forecast during the air quality simulation, but we need emission forecast. And we combine also different formats, spatial resolution, and so on. Veracity, so it's required. So I don't speak. You will have also a specific webinar on this part about filtering and denoising data. We need also to think in this full chain what's happened in case of missing data, what's happened if we have not the observation for any reasons, if we have not the forecast, if we have not one member of the ensemble forecast. So it's important also to have an approach to fix when we have some problems. And also, yes, you see some results of the machine learning approach on one industrial site, but of course there is this machine learning approach must be applied on a variety of industrial sites, of climatologic situation. So it's we can speak about veracity. And value, yes, because first it's to treat air pollution and manage air pollution. So there is environmental value, and also, and perhaps most important also for industrial sites, we have financial value because the objective is to apply the best strategy for the sites based on the robust data, avoid false actions, which means extra financial cost. Thanks to have followed this webinar.